In this active analog filter designed using 3 ideal op-amps, 1, 2, 3, we want to find the voltage transfer function V out over V in as requested. Let's make the assumption that properly biased op-amps we have here in terms of applying the positive negative voltage supplies so that op-amps are a linear region of operation and therefore virtual short is valid for each of the op-amps. By that I mean the voltage at the positive input terminal is the same as voltage at negative input terminal. Therefore, if we have 0 volt here at positive terminal of op-amp 3, we have also 0 volt at the negative terminal of op-amp number 3. So the same thing, if at node X here, if we have voltage Vx, therefore Vx appears at negative terminal and therefore Vx appears at the positive terminal, so it would be here. That means that Vx is at this negative terminal. As a result, for the same reason that op-amp number 2 is in linear region of operation, it means Vx would be at positive terminal, would be here, therefore Vx. On the other side of this resistor is 0 volt, therefore the current I that is flowing through this resistor is computed easily. I is Vx divided by R. So let's name this equation number 1. Okay, so this current I cannot be supplied from the input terminal of op-amp because no current can flow there. This current I has to directly come from the other resistor R. This resistor R is the same value as this resistor R. Therefore, since these two resistors not only have the same value, but also on one side they have the same voltage and on the other side they have a common node, as a result of that, what happens is the same current that is flowing through they should have the same current basically. That's the meaning of it. They should have exactly the same current. So if I is flowing here, I should be flowing through the other one as well. So this I goes through this guy and continues flowing through this resistor and then getting to this node, but then it cannot go through the input terminals of the two op-amps connected, so this I has to keep continuing through this C cap. So as a result, we can compute the voltage drop across cap easily, Vc. Now, the nice thing is this cap should have the same voltage drop across as this resistor Kr because they have the same node at one side, which is node Y. So let's name this node Y and therefore voltage Vy. And on the other side of the cap, we have Vx. And on the other side of Kr, we have also Vx. So therefore, the voltage drop across cap and also Kr is the same thing. For the cap, I know the current I is flowing through it. So I times 1 over Cs, that's the voltage across cap, should be equal to voltage of the resistor Kr, which is Kr times, let's name this current that is going through Kr as current I2. So let's name this as I2. Therefore I2. So what I obtain here, if I use equation 1 to substitute for I, then I can say Vx over R times 1 over Cs is equal to Kr times I2. So as a result of this, I can say I2 is equal to Vx over R squared Cs. So let's keep this as equation number 2, which is very useful. Now, let's focus on node X, which has a voltage Vx. I can write a KCL at node X. So KCL at node X. Let's assume that the current I1 is flowing in from the input of the circuit. That I1 is coming in, should be equal to I2, and then the other branch doesn't have any current because it's going through the input of op-amp. So therefore, as a result, I can say the only other current is I3 that also continues going through the cap because it cannot go through the input terminal of op-amp. So what I can say at node X is I1 is equal to the sum of the two other current that are going out of the node X. Now, substituting for that, I1 is simply Vin minus Vx divided by the resistor in between. So it's going to be Vin minus Vx divided by resistor R equal to I2 is the one that I found from equation 2. So I'm going to use equation 2 to substitute for I2, which is Vx over R squared Cs. And then for the I3, it's simply Vx minus 0 divided by the resistor in between R. So Vx minus 0 divided by R. Alright, so simplifying everything that I found here, I got this nice outcome that I can cancel out R like this, and then I can write Vn, then I can write as simple as this. Vn is equal to effectively 2 plus 1 over, and what I missed is, did I miss anything? Yes, I did. I missed K here. So be careful about that, not to make that mistake. So K RCS times Vx, reshuffling things around. Vx is equal to basically Vn divided by 2 plus 1 over K RCS. So this is my equation number 3 that I'm gonna keep and use later. So, okay, what is the next step? Next step is just writing the fact that this current I3 is flowing through both resistor R and also through the cap C. So I can write this fact that I3 effectively is equal to Vx minus 0 over R and is equal to 0 here minus, if this node is Z, I can say 0 minus Vz over 1 over Cs, which is this cap in between 0 and node Z. So I just want to record that Vx is equal to negative RCS times Vz. Or, say it in another way, Vz is Vx divided by negative RCS, or negative Vx over RCS, doesn't matter. So that is the equation number 4 I want to keep, but at the same time, let's keep that, it's okay, I can combine it with equation 3 later. Last step, I can write a KCL at node Z. So KCL at node Z, which means the current I3 that is going this way is equal to the current IC, is plus the current IC is equal to the current IR. So I3 plus IC should be equal to IR. And then now I'm going to use different things here. So I can say, okay, I can say for I3, 0 minus Vz divided by 1 over Cs plus IC, I'm going to use, so what I use here is for IC. For I3, I'm going to use equation, let me just make sure I'm doing it right. Okay, so for I3, I did it right. For IC, I'm going to do V out minus Vz divided by 1 over Cs as well. And finally, for IR, I'm going to do Vz over R. Okay, so as a result, what I can summarize is as simple as this. V out minus 2Vz, or V out equal to 2Vz plus just to make sure I'm not missing something, plus 1 over RCS Vz. And I can factor out Vz, of course. Now, what I'm going to do is I'm going to use combination of equation 4 and 3. So I'm going to substitute Vz from equation 4, and then I'm going to substitute Vx by equation 3. So using equation 3 and 4, I get V out is equal to minus, just to make sure I'm not dropping anything, 1 over RCS times 2 plus 1 over RCS divided by 2 plus 1 over K RCS. So in summary, I'm going to write it here, in summary, and times V in. V out over V in, the transfer function, voltage transfer function, is simply minus 1 over RCS. And let's just make sure I'm not missing something, because there are so many variables involved here. So I can say minus 1 over CS, and then what I get is 2 RCS plus 1 divided by 2 RCS plus K, plus 1 over K. I think that's the outcome. So this is the desired voltage transfer function that we were looking for to find for this circuit. I hope that the analysis presented in this circuit that is seemingly a little bit involved, but effectively if we follow the flow of current would be easy to analyze, is helpful, so that we can see how we can find the voltage transfer function given in this circuit. I hope this is helpful.